Scientists reading mud from the floor of the Pacific have found that the earthquake the American West Coast is waiting for may not arrive alone. 3,100 years of seafloor cores, and inside them, 3 separate times in the last 1,500 years when 2 of the largest faults in North America appear to have gone off together, the most recent of them in the year 1700, possibly within minutes to hours of each other. 2 ruptures in the same window means 2 disasters landing on the same emergency system at the same hour. One shaking the Pacific Northwest and sending a wave at the coastline, the other tearing north and south through California. For decades, those 2 faults were treated as separate problems on separate maps and separate emergency plans. Cascadia was Oregon and Washington's nightmare. The San Andreas was California's. But the sediment does not appear to respect that division, and the work published in the last 12 months is the reason anybody can say so with confidence. Later in this, how a Japanese diary dated an American earthquake to a single day more than 300 years ago, and why the mud that holds this entire record could not be trusted at all until January of this year. But first, what the cores actually show. The finding comes from Oregon State University, led by the marine geologist Chris Goldfinger, published in the journal Geosphere in 2025. The team read turbidites, layers of sand and mud dropped on the deep ocean floor by underwater landslides that big earthquakes set off. Stack enough of them, and the seabed becomes a filing cabinet of every great quake that ever hit the margin. What Goldfinger's team found in that cabinet were reversed patterns they call doublets. A doublet is the signature of 2 earthquakes arriving close together rather than one event followed by centuries of quiet. 3 of them show up in the past 1,500 years. And the most recent one is the event everybody in the Pacific Northwest already knows by heart. The co-author list is worth hearing because it shows how many institutions had to agree on this. Anne Morey, Christopher Ramsos, and Brand Black from Oregon State's College of Earth, Ocean, and Atmospheric Sciences, Jeff Beeson from NOAA, Maureen Walskak from the University of Washington, Jason Patton from the California Department of Conservation, Hans Nelson and Julia Gutierrez Pastor from the Instituto Andaluz de Ciencias de la Tierra in Spain. And here is the sentence that does the damage. Goldfinger, describing what one of these events would demand, said, "We could expect that an earthquake on one of the faults alone would draw down the resources of the whole country to respond to it. One of the faults alone." Now, the caution that has to sit right next to that, because the study is careful and the video will be too. The paper says the faults may trigger one another. It says 3 events show potential synchronization. It is a pattern read out of sediment, not a proven mechanism, and not a prediction. Nothing is happening right now. There's no swarm, no alert, and no forecast anywhere on either fault. It is worth being clear about what these 2 faults actually are, because they are not the same kind of machine. Cascadia is a subduction zone. One slab of ocean floor is being forced underneath the edge of the continent, jamming as it goes, and when the jam finally slips, the whole margin lurches and the seafloor moves vertically, which is what builds a tsunami. The San Andreas does something different. It is 2 blocks of crust grinding past each other sideways, which is why it tears through the middle of California rather than sitting offshore. Different mechanisms, different failure, different disasters. They meet near the northern end of California, and that is the neighborhood where these doublets show up in the record. What the research does not claim is a mechanism. Nobody in these papers says, here is the physical process by which one fault sets off the other. What they say is that the sediment shows the 2 arriving together more often than coincidence comfortably explains, and that this deserves to be planned for. That distinction matters, and it is the difference between science and a headline, which raises the obvious question. Mud on the seafloor gets moved by all sorts of things. A winter storm can drop a layer. A flooding river can drop a layer. So how does anybody know a given band of sand was laid down by an earthquake and not by weather? For decades, nobody could fully rule it out. That was the weakness at the heart of this entire field. Then, on the 19th of January this year, a paper in Science Advances closed the gap. The lead author is Jenna C. Hill of the United States Geological Survey, working with the Continental Margin Processes team and the Seafloor Mapping Lab at MBARI, and with the USGS Pacific Coastal and Marine Science Center, a partnership that has been running since 2020. They went to the seafloor off Crescent City, California, with autonomous underwater drones and tethered robots, and they mapped where the sediment actually comes from. The answer was that the deep abyssal layers are fed primarily by failures on the lower slope, a source that a storm cannot reproduce. That is what turns a suggestive layer of sand into evidence. It is worth pausing on how that work was done, because it is not a boat dragging a tube through the dark. The teams have been at this since 2020, sending robots down to build maps of the seabed detailed enough to show where each landslide started and where its material came to rest. Only once the source of the sediment is known can a layer be tied to a shaking event rather than a rainy season, and the method is not limited to this coast. The authors point out that the same approach can now be turned on subduction zones anywhere in the world, which means every megathrust with a muddy floor just became more readable. And the pattern they mapped is not local. It runs across 600 miles of margin from Northern California all the way to Canada. Their reading of that record, a major earthquake on this fault, on average, every 500 years. The last one was in 1700, which is where the Japanese diary comes in. Nobody in North America wrote the date down. There was no instrument, no seismograph, no colonial record on that coast. What there was, on the other side of the Pacific, was a country that kept meticulous documents, and a wave that arrived at Japan's Pacific coast with no earthquake felt beforehand. Japanese records call it an orphan tsunami, a wave with no parent. The destructive waves came ashore on the 8th and 9th days of the 12th month of Genroku 12, which converts to the 27th and 28th of January, 1700. Maximum wave heights on the Japanese coast are estimated at about 7 to 16 feet. Run the crossing time backwards across the Pacific, and the parent earthquake lands on the 26th of January, 1700. Its magnitude is estimated between 8.7 and 9.2. That is how an American earthquake got a birthday, written by people who never felt it, more than 4,000 miles away. So, what are the odds of the next one? The United States Geological Survey puts the chance of a full margin Cascadia earthquake, the roughly magnitude 9 version, the whole fault at once, at 10 to 15% in the next 50 years. But that is only the biggest version. The southern section, off Oregon and Northern California, produces magnitude 8 earthquakes more often than the full margin ones do. So the chance of some great Cascadia earthquake inside 50 years is considerably higher than the headline number suggests. And on the other fault, the clock has been running longer than most people realize. The 1857 Fort Tejon earthquake was a magnitude 7.9, and it ripped roughly 220 miles of the San Andreas. But that was one stretch. The southern segment, running through the desert north of Los Angeles, last produced a major rupture around 1680. The southernmost stretch, down by the Salton Sea, last went around 1690 to 1700, more than 3 centuries ago, against an average repeat time of roughly 150 to 200 years. The Mojave segment alone carries a 19% probability of a magnitude 7.5 or greater in the next 30 years. That is the highest figure attached to any single fault segment in California. The 2015 forecast, known as UCRF3, put the odds of a magnitude 6.7 or greater at 72% in 30 years for the San Francisco Bay Area and 60% for Southern California. Zoom out and the picture stops being a coastal problem. According to the latest USGS national model, around 75% of the United States could experience damaging earthquake shaking. Now put the two faults back in the same sentence and ask what one Cascadia rupture on its own would do. FEMA has already answered that, and the answer is on paper. In June 2016, the agency ran an exercise called Cascadia Rising, modeling a magnitude 9 event, the most comprehensive federal emergency exercise ever run for an earthquake. The scenario figures: more than 13,000 people killed and close to 1 million displaced across Oregon and Washington. Those are modeled numbers from a planning exercise, not a forecast, and they deserve to be labeled that way every time they are used. But they are the official scale of the problem, and they describe one fault moving. The doublet research asks the question nobody's plan is built around: what if the second one starts while the first is still shaking? Because the response to a disaster of that size is not local. It is national. Aircraft, hospitals, engineers, generators, water, search teams, all of it converges from the rest of the country toward the damage. That is what Goldfinger meant about drawing down the resources of the whole country. A second rupture in California, minutes or hours later, would not just double the damage. It would land on top of the machinery that was supposed to arrive and help. And the geography makes it worse in a specific physical way. The routes that would carry aid into the Pacific Northwest come up through California. Bridges, highways, ports, fuel lines. A second earthquake on the San Andreas does not merely create a second disaster zone. It can sit directly across the road to the first one. None of that is a prediction. It is a scenario that the sediment says has already happened at least 3 times, and most recently in a year we can name. There is one more reason this particular pairing is uncomfortable. Each of these faults separately is already among the most studied and most planned for hazards in the country. Oregon and Washington have run Cascadia exercises for years. California has spent decades retrofitting for the San Andreas. Both sets of plans quietly assume the same thing: that when the worst day arrives, the rest of America will still be standing and will come. 2 ruptures in one window is the one case that assumption does not survive, and the timing cannot be narrowed. An average of 500 years between Cascadia events does not mean a due date. It means the intervals in the record vary widely around that number, and the last one ended 326 years ago. That is a long way into the range, and nowhere near the end of it. Anyone who converts that into a countdown is inventing something the science does not contain. The honest state of the science is this: two faults, side by side, each capable of a catastrophe on its own. A 3,100-year record that shows them arriving together 3 times in the last 1,500 years. A brand new confirmation from January of this year that the record can be believed. And a probability that nobody can convert into a date because earthquakes do not run on schedules. They run on averages, and an average is not an appointment. The last time the pattern showed up, it was 1700. Both records, the mud off the American coast and the ink in a Japanese ledger, agree on that year. Subscribe for the real numbers on the next one.